I'm Antonin, and I'll be talking about aggregated tests using kernel-based methods, so using the MMD and the KSD. So first I'll talk about two sample tests, and then I'll explain how the same idea can be used for a goodness of fit test. So yeah, as I said, I'll start with the aggregated two sample test. So this is joint work done with my two supervisors, Benjamin Guedj and Gretton, and collaborators Delvin Kim from Yonsei University and Mélisande Lambert and Béatrice Laurent from University of Toulouse. So a two sample problem, what is it? We're given samples x1 to xn drawn ID from density P, and samples y1 to yn drawn ID from density Q, and we're interested in deciding whether P is equal to Q. So we're really testing the null hypothesis that P is equal to Q against the alternative that P is different than Q. And so this can be interesting, for example, in drug testing. I have some drug, and they take some data, then they take some data, then they apply the drug, then they take data again, and then they can check does the data come from the same distribution? So did the drug have an effect or not, for example? And so a statistical test, which is a function capital delta, that's just a function that takes as input the data, and it outputs 1 if we reject H0. That means we think that P is different than Q, and output 0 if we think that P is equal to Q. So by design, the hypothesis tests control the type 1 error. So type 1 error is under the null hypothesis when P is equal to Q. What is the probability that we make an error so that we reject the null hypothesis? And this the test in general by design control this probability by some alpha, which is some number smaller than 1. And then for type 2 error, we want to find a condition on the norm of the difference of identities, P minus Q, to control that probability of making an error. So the type 2 error now is when P is actually different than Q, but our test is going to think that P is equal to Q. And we want to bound this by B2. But clearly, you cannot bound both of these errors to be very small. Like if one increases, the other one decreases. And so for this one, we really want to find a condition on the norm of P minus Q, because if P is extremely close to Q, and because you only have access to finitely many samples, there's no way you can actually distinguish. So that's why it should depend on this norm. And so we'll be doing a two sample test using the maximum mean discrepancy. So maximum mean discrepancy is a measure between probabilities. So like the KL over Washer's time distance. So first we introduce some kernel. So if you're not familiar with kernel, you can just think of it as a function that takes two inputs and outputs a real number. And here we work with a kernel, so in dimension D, and it's just a product of one-dimensional kernels, and those are those functions ki, and they're evaluated at xi minus yi divided by this bandwidth term, such a translation invariant kernel. So that's what we assume. And the lambda parameter in orange is called the bandwidth, and we're going to see that this whole talk is going to be about the choice of bandwidth and how we can solve this problem. So then we can define the maximum mean discrepancy, so the MMD. So it's defined as the supremum over some RKHS. So you can think of this supremum just as being a supremum over some space of smooth functions, essentially. And then you want to take the difference in means, so that's why it's called maximum mean discrepancy. So the first one is the mean under P of a function f, and you want to do minus the mean under Q of a function f. And so that function f, so that's how the MMD is defined. So to try to give some intuition about this witness function f and the role of the bandwidth lambda, I'll just show some examples. So let's say we have the case where p is different than q. So those are the samples you get in red from q and in blue from p. And if you use a bandwidth that's too small, essentially can be shown that this function here, what's plotted is the function f, essentially that where the supremum is attained. And so we really see that what this function is trying to do is trying to make all the points in red quite be as small as possible in a negative way, and then all the point in blue to be the furthest possible up, so that the difference in the mean is going to be the biggest. But yeah, and this function can be written as a sum of essentially the kernel evaluated at those points. So that's why you see bumps at every point. So this is the case where you have some bandwidth which is too small. And then if you have, let's say, a well-calibrated bandwidth, then you would really have this thing where, as it shows, it's quite smooth, and it goes under. For the red points, it goes down, and for the blue points, it goes up. But if you have a bandwidth that's too large, then you're not going to be able to detect anything, because essentially, yeah, because the bandwidth is so large, like the MMD is not going to be high anymore. So that explains why the bandwidth is important for a case p different than q, and for the case p is equal to q. If you get a bandwidth that's too small, essentially you're going to be able to detect some noise. So here, both points are drawn from the same distribution, just a uniform one, but with a very small bandwidth, we can still put like bumps towards up and down above the red and the blue points. So that's not something we want to be able to do. And so if we have a well-calibrated bandwidth, then we get quite a flat witness function. So we'll get a small MMD, so that means that p is close to q. And if the bandwidth is too large, we'll get something basically flat. So hopefully I've convinced you that the choice of bandwidth is very important for testing, or at least intuitively. And so in practice, how do people choose this bandwidth parameter? So there's two main methods. So the first one is you just use a heuristic, for example, the median heuristic or some standard deviation. So it just means that you take all your data, you look at the distance between the L2 distance between every pair of points, and you take the median of those. But there's no theoretical guarantees with it. It's just a heuristic. And the other approach is to do data splitting, where so you've given your data, you split it in two halves. You use one half to select your bandwidth, where you can maximize some criterion, and then you use the other half to run your test. So one issue with that is because you split your data, at the end of the day, you run your test only on half the data. So you have a less powerful test just because of that. And so what we propose in this paper is to aggregate multiple tests with different bandwidths. So I'll explain how we do that, and I'll show that it works better. So the maximum mean discrepancy can also be shown to have this form, where it's some expectation of a kernel under P minus twice some expectation of a kernel under P and Q plus the expectation of a kernel under Q. And so we can get an estimator. So this was for the real like P and Q, which we don't have access to. In practice, we have access only to the samples, XM and YN. And so we can just replace those expectations with some U statistics. So essentially, we just estimate those three terms. And so we can get an unbiased estimator for the MMD. So once we have this unbiased estimator, we're going to reject the null hypothesis that P is equal to Q if the MMD we've computed is greater than some quantile, and we need to approximate this quantile. And this is a 1 minus alpha quantile, and the way we do that is we need to simulate the null hypothesis. So we can do this by using some permutations. Essentially, so yeah, we take all the points, we just put them all together, we permute them, and then we split them in two separate sets again. And because we've done that, then they'll have the same distribution. And that's what we want to simulate, is that xm and yn have the same distribution. So to compute this quantile, we just obtain B permuted statistic, where, as I said, we just permute the samples and compute the MMD. And then we also throw in the original sample, and we take the B plus 1 times 1 minus alpha largest value. And we show that this gives you some non-asymptotic level alpha. So that's great news. That's what we want for the test. So that's just a normal test for a fixed bandwidth, by the way. And then I'll explain how we do it for when we aggregate the bandwidth. And the time complexity of doing this is B times, so B is just a number of the permuted test statistic we have to compute, and the m plus n squared is quadratic time. It's just the cost of computing some this MMD estimate. So that was for a fixed bandwidth, and so what we propose is to do that for a collection of bandwidths. I'm going to explain how we can do that. So it's essentially quite similar, but now we propose to reject the null hypothesis if the MMD is greater than the quantile like before, but for some lambda in the collection of bandwidth we consider, capital lambda. And here we need to correct the levels, because otherwise we no longer have level alpha. So we introduce some positive weights. Those are just some weights that with some smaller than 1, and some term U alpha, which is designed so that our test exactly has non-asymptotic level alpha. And so essentially, if you look at this, it looks a bit complicated, but it's not really. So up there you have MMD greater than quantile. That's the same as saying that MMD minus quantile is greater than 0. And it's for some lambda, so that's the same as saying that the greatest value of MMD minus the quantile is greater than 0. So essentially here, that's the probability of rejecting the null hypothesis. And you want to do this under the assumption that P is equal to Q. And then you want to bound this by alpha. And here we have this parameter U, and we take the supremum over the parameter U. So by defining it like this, if we can calculate this U alpha like this, then we have a test of level alpha. And so I said, before I talk about the complexity, in practice, the supremum we cannot compute exactly, so we need to use some root bounding methods. So we use some bisection method to find the root to compute the supremum, because essentially this is just some function depending on U, this whole thing, and we wanted to find the root with minus alpha to find its root. And the probability P under the null hypothesis, that's this term here, we want this. Oh, sorry. So we also approximate this using permuted the statistic like I presented in the slide before. So the overall cost of our algorithm is going to be the number of bandwidths times the cost of computing all the permuted test statistics. So that's the m plus n squared is the cost of just computing one, and then we have B1 of them that we use to estimate our quantiles, as I explained on the last slide, and we use B2 of them to estimate that probability using a Monte Carlo method. So that's how we've defined our tests, our aggregated test MMDAgg. So again, go quickly through this. I don't know how much time I have left. So in our paper, if you're interested, you can have a look. We essentially prove that our test is minimax optimal over Sobolev balls. So Sobolev balls are defined above. essentially a spacer function. I won't go into details. And so this is important if we show that for this specific collection of bandwidth, which is just some powers of 2. So the bandwidth is a d-dimensional vector. And so that's 1D, open that. And then we just take powers of 2 of this, decreasing powers of 2. And we show that for if we take this number, so L ranges from 1 to that guy here. But what's crucial about this is that for the Sobolev balls, you have a smoothness parameter S that's in green up there. You cannot read your green, but and this smoothness parameter is unknown. And here, the collection of bandwidth we consider does not depend on any smoothness parameter S. And nonetheless, we obtain almost the minimax rate. So this is the minimax rate of the Sobolev balls. And we observe that we obtain the minimax rate up to some log term. And what does the minimax rate mean? It's just some condition. So it means that if the L2 norm of the difference of the densities is greater than this term, then we can guarantee that our test has a probability of type 2 error bounded by beta. How much time do I have?
2 minutes.
2 minutes, okay, moving quick. And so just I'll do the experiments. So we run our experiments on MNIST, so lots of numbers. And so what we do is, as for P, for one of the densities, we use just all the numbers from 0 to 9. And then for the alternative, we remove some even digits. So Q1 will be all the numbers except 8, all the way to Q5, where Q5 is only the odd numbers. And so as we move on the x-axis from Q1 to Q5, the problem gets easier and easier, because it's easier to distinguish between odd numbers and odd numbers rather than odd numbers and odd numbers without 8. And so the 4 different tests we consider are, so our aggregated test, the test that uses the median heuristic that I talked about at the beginning, the test that splits the data, to split the data in 2 halves, and it chooses the bandwidth on 1 and runs a test on the remaining data. And we also compare to this MMD split extra, which essentially has access to some extra data to choose an optimal bandwidth. And so in the experiments, we observe that our aggregated test performs as well as the test which has access to some extra data. So we're really pleased to see that. And I think that concludes my talk. If you're interested in the work, you can come to the poster session and I can talk about the goodness of the test as well. Are there any questions?
So I have 2 conceptual questions. One is first one is bridge kernel, and the second one is in early slide. I'm not sure if you just wrote that in simplicity, but you wrote a translation variant kernel. So I'm just always wondering what's sort of the efficacy of the translation variant kernel, and what context can you use them?
Yeah. What was your first question again?
What's the kernel?
So in the experiments, this one is just a Gaussian kernel, but in the experiments we also use the Laplace kernel. But in our paper, we're very generic about the kernel you can use. So this theorem we proved actually holds for any translation invariant kernel that belongs to L1 and L2. So that's like integrable and square integrable. That's the only, so it doesn't need to be bounded. It's the only restrictions we have. And regarding why is it important for this result to hold, that we need the translation invariant kernel. So that's going to be because of a Sobolev law. So if you look at the definition of a Sobolev law, there's some Fourier transform in the F there. I'll run quickly some other slides.
Maybe I could paraphrase the question, but I don't think it's necessarily, maybe it's required for your proof, but why in general should one care about using translation invariant kernels?
So I'll just explain very quickly for the proof, and then I'll go back to it. So the main idea is in the proof, here we have some term like that, where this is a convolution. And essentially by going into a Fourier domain, we're able to work with this convolution. It's just going to be the product of a Fourier transform. So that's why it's easier. But in order to do that, we need this to be a convolution. And for this to be a convolution, we really needed the fact that the kernel is translation variant. In general, for hypothesis testing, why do we need
maybe sometimes it's better to use non.
Yeah, I need to think about it, honestly. I can't give you a very good answer. But yeah, maybe it's the case that it might be better not to use. I don't have a good intuition.
Isn't the KSD or MMD with non-translation invariant kernel? So then you don't have to.
But sorry?
So the KSD, I have obviously haven't seen the rest of the presentation, but you can think of the KSD as an MMD with a non-translation invariant kernel.
Yeah.
So in that sense, for your question, you don't have to use translation invariant.
No, we don't have to use definitely no. So that's the point actually. So that was this is the result for the KSD. And essentially for the MMD, that's one of the steps for the MMD. For the MMD, because it's translation invariant, we're able to go further, go into the Sobolev domain and work it out. But yeah, sorry. So if your question was, does your test, the test works for any kernel essentially, but it's really the theoretical guarantees hold that we prove they hold only for translation invariant.
Okay, sure.
So you can use the test with
sure, but then like my question is more like what? So is it better to use translation invariant?
I don't know. I need to think about it. Any other questions? Yeah.
Question about the previous year, slide 6. About the condition of assuming that the difference is in the Sobolev. Can you talk about that a little bit? The restrictive condition?
So that's really essentially when we think about the minimax rate, we really need some assumption on P minus Q. So P minus Q, you can think this is like a kind of a perturbation. You have your density P, and then maybe Q is just a perturbed version of P, and you want to detect that perturbation. So if you make no assumption on the smoothness of that perturbation, then you're not going to be able to prove anything, because if a perturbation is really not well behaved, and let's say it's extremely small, then there's no way you'll be able to detect that thing. So you really need an assumption on the smoothness of this perturbation. And here the assumption we use is that it lies in the Sobolev for some parameters S and R. So the whole point of our test is that it's adaptive to this unknown smoothness parameter S and R.
Great. Okay, folks, let's thank Antonin again.